Good morning, good afternoon, or good evening, depending on where you're based. Thank you very much for joining us. We're really excited to deliver this Connection Wednesday webinar, as it is it's just a few days since we released the new version, 21. And we have some very exciting things to show you regarding further improvements and innovations for the still module that basically justify what actually the webinar title says, Still Connection Design for the 21st Century. My name is Theodore. I have Kostis with me today, who is going to do the biggest part of the presentation. Before we start, as usual, for those of you who haven't used GoToWebinar previously, you are all muted by default throughout the session. But if you have any questions, you have a panel on your right side of your screen, so you can enter any questions you might have during the webinar. We will make sure to answer all those questions either through the chat or depending how much time we have at the end of the webinar. The new features of version 21 have been more or less covered by a previous webinar we did. So for those of you who missed it, you can find it on our website or our YouTube channel. Today, we're going to focus more on the still module and specifically on the improvements that we have done in the analysis and simulation of the connection, which is a key element in our software, if not the most important one. Let's quickly go through the agenda, what we're going to see today. So first of all, we have an increased accuracy for slender circular hollow sections according to the latest developments. We also have an increased solution accuracy by capturing effects like warping in the new version, which is important, as you probably know. We also have reduced calculation time by around 30%, simply because we have a reduced model size. And because of that, we also have a faster result recovery and visualization because of this reduced model. Now, before we proceed to the new features, let me quickly go through the features that we have already introduced in the previous version. So in the 10.1 release, we have already introduced geometrically and materially nonlinear analysis. This adoption was a first step towards a more accurate calculation of slender hollow sections. And we will see later on how we further improve this. In release 21, the GMNA, geometrically and material nonlinear analysis, now applies not only on the member, but on links and constraints. Further to that, a big innovation is the introduction of the condensed super elements, which is, these are elements that are actually invisible to the user, but they have really a very important function. And let me show you a little bit more how this works. Now, as you can see in the version 20.1, these restraints have been acting on the member, and depending on the different cross-section, we have a different length. So for hollow sections, we used to have 2 times the height of the cross-section, and for open sections, we have 1.5 times the size of the cross-section. In the new version, with the condensed super elements, what we actually did is that we introduced smaller member lengths, and we have now the same size for the member, which is 1.25 the height of the cross section. As a consequence, fewer shell elements are required. So that leads, as I mentioned earlier, to the 30% faster calculation times. A further improvement from the introduction of these condensed super elements is that these super elements allow the member ends to deform freely. And this prevents the development of unrealistic stresses at the member ends. Now, before we continue, it would be very interesting for us to run a quick poll regarding our newest version. So I'm just going to quickly run the poll. So please answer, what IDEA StatiCa version are you currently using? Of course, if you're not a user, you can simply choose the last option. So I'm just going to leave this poll a few seconds on your screen. Okay, I see that most of the votes have come already. Thanks a lot. Excellent. Okay, I'm just going to close the poll and let's see the results. So we can see that most of you are actually using the latest version. That's really good. And just a very small percentage is using older versions. I hope that this webinar will convince you to move to the latest one. And it's also interesting to see that many of you are not customers, so that's also important for us so that you can see what IDEA StatiCa can do when it comes to connection design. Great, so let's continue with a live demo. So I'm going to switch over to my colleague Kostis, who is going to dig deeper into these innovations.
Thank you, Theodore. I will share my screen right now.
Excellent. I think we can close the cameras as well, just to save some bandwidth. And as they say, the floor is yours.
Thank you very much. I hope you can see my screen.
Yes, excellent.
First, let me comment on the results of the poll. It is a pleasure to see that many of our users have already migrated to the latest version. And right now, I will take it from where Theodore stopped, and I will demonstrate the changes he has already presented to us. And to do so, I have already opened two IDEA StatiCa windows side by side. So to the left, I have opened the previous version 20.1, and to the right, I have opened version 21. And here I have prepared a project, and I have two models that are identical on both versions of IDEA StatiCa. I'm trying roughly to put them in scale by manually zooming in and out. And for this identical model, the first thing that is obvious is that in the new version, we have the model is smaller due to the changes that Theodore mentioned. So we have smaller member lengths everywhere. Now, let's move. Another thing I would like to comment is that these models are idealizations. So, for example, the hollow section I have used as a bearing member is really slender, and later on in my presentation, I will give you a measure of its slenderness. So I'm right-clicking on it, and you can see that it has an outer diameter of 400 mils and a thickness of only 4. Now, for this slender cross-section, let's compare the results between the two versions. And in order to have a better overview of the results, it's better to activate the strain check, plastic strains, and also activate the deformed shape under a scale of 15. I will do the same for the other model, where again, I will activate the strain check, plastic strains, and again, activate the deformed shape under a scale of 15. Now, the first thing that is obvious for this slender cross-section is that in the newer version, it deforms differently. The impact of this deformation is that we have different plastic stress propagation, and we can see that in the new version, the plastic strains are much more extended. And I will switch the view to the side just to demonstrate how the cross-section deforms differently at the member end. Now, beside the length, the difference lies in the condensed super elements that allow this member to deform. In the previous version, we were moving the member to the end using constraints. However, these constraints were also constraining the member from deforming, and we had an impact to the region of the connection. Now, this change is also influencing other kind of problems. I have again prepared an idealized problem using short stubs. So I have created this connection, and which is I have a beam which is loaded in high shear. So let me activate the strain check in this case and decrease the scale of deformation a little bit. Where we see that the problem in this case is that the member fails, but the failure is away from the connection. Now, in previous versions, this was a problem because in reality, we as connection designers are interested in this region of the connection. Now, let's see what happens in the new version. I will activate the overall check, the strain checks. Again, I will decrease the scale of deformation so that we can compare the same things. And right now we see that we have a stress concentration due to the loading. However, we do not have a failure. And the reason, again, is the way that this member head was constrained. You can see this from this jump in the deformation. Another impact in these types of connections is that in the latest version, we have a much more natural and much smoother deformation. And in some cases, this can improve the behavior of the column web panel here. However, one thing you should keep in mind is that in both versions, the region of the connection is identical. Okay, so I will move back to hollow sections, where besides the analysis that Theodore mentioned, we have also improved the checks. And before we move to the improvements we've made, it should be beneficial to discuss some background information about how these hollow checks are made from the code authors. So some types of connection topologies are created, and experiments or advanced numerical models are created. The resistances of these topologies is calculated for multiple modes of failures, and the results of these resistances are curve fitted so that the code can provide resistance formulas for these results. In this slide, we can see in blue color one such curve that is produced from the averaging of all these results. And we can also see a formula that represents the resistance for a specific failure mode. We can also see circles that are the calculated resistances from experiments and or advanced numerical models. One thing that is also important to know for this kind of formulas is that there are regions on these diagrams where we don't have data and where we extrapolate the result from the data we have in other regions. So so near the ends of these diagrams, in case we do not have experimental results, the accuracy of this relation is decreased. Nevertheless, we have produced plenty such formulas for multiple modes of failure and, of course, multiple connection topologies. This set of formulas is called the failure mode method. And the very important thing about this methodology is that it is developed and promoted by an international association called CBFEM. The importance of this thing is that it is widely adopted all over the world, and it is adopted in many in the most important codes. Let's see what we did in the latest version of IDEA StatiCa in this front. So we have calibrated the models against the most recent version of this set of formulas, which is also adopted in the draft of the latest generation of Eurocodes that will be published in the future. So what we did was that we created a reduction coefficient for the shell bending resistance of the shell elements, and this is related closely to the cross-section slenderness. And the measure of this slenderness is the gamma value you can see below. And as this value increases, the cross-section becomes much more slender. That way, we're able to capture the effects of residual stresses and initial imperfection, but the most important aspect of this approach is that we managed to have very good agreement with the results of the failure mode method curves. In this slide, I am presenting one of our benchmarks, which refers to a T-CHS section topology, where we have used a θ1 value of 90 degrees. And in this diagram, we have a dashed line, which represents the resistance as calculated by the latest code formulas. Around this dashed line, we have some colored circles that represent the results of the calculation from the CBFEM method. Please note that the darker colors have a higher gamma value, which means that we have more slender cross sections. Also note that in this diagram, the more slender cross sections have a very good agreement with the reference calculations. It is also important to see that we have accepted a variation from the reference value of plus minus 20%, while we normally go for a plus minus 5 to 10%, but this is in line with the nature of these results. Now, in case you wonder about the cross section I have mentioned earlier, the gamma value that corresponds to this cross section has a value of 50, which is too slender. And the reason I did this was to enhance this effect and clearly demonstrate the differences between the two versions. Now, at this point, and before we move further, I would like to make a poll and ask your opinion about another effect we see in steel structures, and which is called warping. So I will launch the poll that you will see to your screen. I will leave this for about 20 to 30 seconds. I see that people are voting, so let's wait a little bit more. Results keep coming. Okay, so at this point, let's close the poll, and I will share the results with you. I will leave it a little bit, and we can see here that 53% voted that warping influences open cross sections, which is what we expected, and 17% voted that it influences hollow cross sections, 29% any kind of cross section. So let's hide the poll and move to discuss this a little bit more. So let's put some context into this discussion. We all know that open cross sections are much less efficient in providing torsional resistance in relation to their closed counterparts. The reason is that the shear flow in open cross sections has opposite direction in opposite faces along a section of the member. This creates a stress variation along the length of the element. However, in closed cross sections, we can see that the shear flow has the same direction for opposite faces, which creates a stress variation, which does not create a stress variation, but we have a stress distribution that is near uniform. And this has an impact because open cross sections tend to deform in their plane. However, the closed cross sections tend to remain plane in their plane after they deform. Now, let's move further and see what is warping. In the illustration below, we can see that under the effect of pure twisting, this beam, the flanges of this beam counter rotate in their plane. Now, when the warping of an open cross-section is constrained, this means that additional longitudinal and shear stresses will be developed, and torsion will be partially resisted by these additional stresses that you can see in this picture. It is also important to know that the effects of warping cannot be captured in your global analysis software. The reason is simple. To capture this effect, you need to have elements with a 7th degree of freedom that produce the bi moments. So let's investigate the effects of warping in some reference elements I have prepared for you. And first, let me open a reference model that is using a closed cross section. Again, I will roughly zoom in to have about the same model in both windows. So I will activate the overall check, and in the case of a closed cross section that is loaded under torsion, we can see that the results are almost identical. So let me also activate the deformed shape under scale 5. And we can clearly see that we do not have difference in either the solution or the deformations. And the reason is that these closed cross sections are not susceptible to warping. We have a slight difference, which is due to the overall different deformation of the model. As we said before, now the deformations are much more natural due to the condensed super element. Another important aspect of this model is the bolt forces. So let me activate the bolt forces here, and we can see that the magnitude of the bolt forces is almost equal in these models. We have some slight difference due to the rotation of the supporting column. And let's move to an open section. Here, results are very different. We can already see this from the overall check, where now we have some parts of this model that are in the green area, while in the previous model they were in the gray area, meaning that they were not even plastified at all. Again, this is an idealized model to enhance the differences between the two versions, because we have an open section that is under torsional load. Usually we have open sections under both bending and torsional loads. Now let's see the differences again. And you can clearly see that we have a different rotation in the open section. And in this model, I have also used a very thin end plate. So the end plate also deforms. This influences the welds. And now let's see what happens with the bolt forces. And for the both forces, we can see that we have 2.5 times higher tensile bolt forces in this case. This is also reflected in the checks, where we can see that the utilization is much higher for welds and bolts. As a result, the conclusion is that warping influences open cross sections. Now, let's explore how the changes we have discussed so far influence existing models. As an example, I have to use one recent support case. And as we open these models, let me tell you that we have performed many benchmarks, and on average, we expect to have a difference of less than 1% in these two versions. So this was a simple connection that was designed from one of our users. And before we move and explain things in depth, let me see what do we expect from these two versions. So what we expect is almost identical results. Now, let's see what our user experienced. Again, we have this connection here. I will activate check. And again, activate the overall check. And we can see here, clearly see that there are differences as we have failures in the supporting member. So the question is, why do we have differences between version 20.1 and version 21? Before we move to explain this, let's see what are the differences between my model, which has the expected behavior, and this one. Now, in my model, I have activated the loads in equilibrium. So I have defined loads in every position on this member. And when loads in equilibrium are activated, the supporting member is only supported at a single position. The user, in his version of the model, had equilibrium deactivated. This means that the supporting member is supporting on both ends, and the loading was applied only on the inclined diagonal. Now, to explain the difference in the results, let's start a discussion and investigate a simple analysis model that corresponds to this support incidence. For the sake of this discussion, let's assume that this simple structure is loaded with a uniform load. And this is a very simple structure. We have applied supports, and we can use a hand calculation or an analysis software, which will calculate reactions, and then it will calculate internal forces that vary along the member lengths. Now, the problem of connection design is that we always have to design connections by only knowing the internal forces of the member. Now, if we isolate this part of the structure and create sections, the internal forces are under equilibrium. This means that the vector sum of all these applied internal forces will be 0. In IDEA StatiCa, we have a tool, we have a table called unbalanced forces that calculates the sum of all these applied internal forces, which in this case is 0. However, many users do not define this every internal force, but they define a single internal force, like our user did in this case. So he only loaded the inclined diagonal. In this case, this single load produces some forces that need to be balanced. Balancing these forces means that we will have a stress propagation along the member, and this stress propagation depends on the underlying model, on the underlying CBFEM model. So let's move and in this slide and discuss a little bit the underlying model for the previous version. So roughly speaking, we have a supporting beam that extends on both ends of the wireframe node, and the length is 1.5 times the member height. And for the inclined diagonal, we have a length of 2 times the member height. In the latest version of IDEA StatiCa, we have introduced the condensed super elements. Now, what I forgot to say before I move to the latest version is that the UB section is a continuous member, which means that if it's not under equilibrium, it will be supported on both ends. And then the user loaded the inclined diagonal this way. In the latest version, we have a slightly different model. So we have the visible part of the model, which is much smaller. So for every member, we have 1.25 times the height of the cross section. But we also have the condensed super elements that extend beyond the cross section members. And in this case, if we have a continuous member that is not under equilibrium, then we will have support at the condensed super element end. And then the load is applied on the inclined diagonal. Let's see the impact of this in some diagrams I have created for these small structures. So I have the reference model and the internal force diagrams that are produced by the application of the lateral load. And one can say that all models have similar axial and shear forces at the region of the connection. However, if we look at the models at the moment for all these models, we can clearly see that the moments are very, very different from the reference model. So the out of plane moment is 2.75 times higher in version 20.1 and 5.77 times higher in version 21 than the reference model. The in-plane moment is 0.90 times the reference model one in version 20.1, and in version 21 it's 1.70 times higher than the reference model. So the conclusion is that they are different structures, and this is the reason we need to apply loads in equilibrium, because we need to reflect the results of a reference model. So the conclusion is that in both software versions, results agree if all internal forces are defined under equilibrium from the reference model. However, if you choose to neglect part of these internal forces, then the overall problem becomes ambiguous, even for a simple case like this one. And as we have always recommended, you should use loads under equilibrium, which is the best practice to provide the most accurate results that reflect a certain limit state. So with this, I conclude my presentation, and I will move the presenter to Theo. Okay.
Thank you. I believe that we have answered all of the questions that we had through the chat. And since we're running out of time, I can see only one question that I think it would make sense to answer it. Does the super element incorporates the theory of large deformations, e.g. buckling?
No. The super elements are not do not incorporate this theory.
Okay. Let me see if we have any more questions. Yes, I can see another one that has just come in about the loads equilibrium. How to proceed with column basis? Are the results different in both versions?
Well, no, I don't think so. As I have demonstrated already, if we have the same model, then we expect to have we have many benchmark cases that we check in each release. So the average difference we have, including base plate, I guess, is that we should expect an average of 1%. However, this depends on the type of the connection. For example, if you also have a diagonal, an incoming diagonal in the base plate, then things can get complex, and as I have already demonstrated, you may not enforce the equilibrium equations, and you may have something different. I think that the best option is to discuss specific things, to discuss specific connection topologies, and see how this connection is constructed from the start.
Okay, there is another question as well. Can you explain why in version 21 you have considered a length of about 4 times the height of principal supporting element?
Well, I'm not prepared to answer this question, to be honest. We have a development team and our R&D team that makes a lot of parametric analysis, and they use advanced numerical models. And I guess that after these parametric types of analysis, they came to this value.
Okay, another question. What are the characteristics of super elements? It's a bit generic, I suppose. You can explain a little bit again how do these super elements work?
Where they are, let me move back a little bit. I think that this slide is ideal. So instead of using multi-point constraints, and let me use a pencil. So instead of using, in the previous version, we were using multi-point constraints. So if for example, you wanted to have a shear force at this point, we were using the constraints to constrain the end and transfer the load there. This is roughly it, okay? Now these constraints were preventing this from deforming. So in the new version, we're using the super elements to move the loads. And that way, this allows the member end to deform freely. This is roughly the theory of it.
Okay.
And
Yes.
Yes. Okay. Yes.
Okay. All right. Perfect. I can see that it's already we're already past the webinar time. So there are some other questions that just came in. We'll make sure that these are answered by email. So at this point, so let me just switch to my screen. So after the webinar, we will you will have a short survey. Please take a couple of minutes to fill this. The recording will be available until tomorrow in our webinars section on our website and also on YouTube. And for those of you who haven't used IDEA StatiCa so far, you can get a trial version at our website as well. So thanks again for joining this Connection Wednesday webinar, and we hope to see you all in one of our next webinars. Thanks a lot. Bye-bye.
Thanks for attending. Bye.